In the preceding video, I'm not sure how much of the theory I talked about. I know that if x sub 0 is a 0 of the leading coefficient, then you can divide by a2x, and you would get these expressions. Now, if x sub 0 is a 0 of a2x, then we can factor out x minus x sub 0 at least to the 1 power, and 2 may even be bigger. And once we divide through by it, it's possible that a1x and a sub 0x have x sub 0 is a 0 as well. But so once you simplify them all the way, write them in lowest terms, if you will, we would have x minus x naught to the n2 minus n1, where the n2 is the power in the denominator and n1 is the power in the numerator. And simplifying the other coefficient as well. And we need both n2 minus n1 to be less than or equal to 1. That is, the exponent on x minus x naught that is attached to y prime needs to be less than or equal to 1. And the exponent of x minus x naught in the denominator of the coefficient for just y needs to be less than or equal to 2. If these conditions are met, Frobenius' theorem says that we have at least one solution of the form x minus x naught to the r times the summation of a normal power series. So the stuff that makes it non-power series is factored out to the front. If these conditions are met, x sub 0 is called a regular singular point. And in this course, we are going to satisfy ourselves with x sub 0 equals 0 in this course. Nothing changes really if you don't have 0 for x sub 0. Everything just gets shifted to wherever x sub 0 would be the center. So this, to let everything x sub 0 equals 0 in all of our cases, only makes the computations more bearable, but it doesn't change any of the theory. The theory would be the same if x were not equal to 0. All we would simply do is change all of our series from x to the r times a sub k x to the k, and we would simply substitute x minus x sub 0 in those spots. That's really all that would happen. So I want to do another example because I don't want to do more than one example in one particular video, because these things are so ridiculously lengthy that I think one is enough. So here, let's do another equation. 2x squared y double prime plus 3x y prime plus 2x minus 1 times y, and that's equal to 0. So before I do anything else, I want to see if I can use Frobenius' theorem to solve this equation. So the first thing we need to do is to divide by 2x squared. And simplify. That's important. We need the exponent on x to be less than or equal to 1 when the coefficient is simplified, and we need it to be less than or equal to 2 when the coefficient for y is simplified. So let's divide everything by 2x squared, and we get the following. Y double prime plus 3x over 2x squared y prime plus 2x minus 1 times y, and that's equal to 0. Oops, I forgot the x squared here. This right now, this exponent is too much. The 2 is too big. However, when I simplify, that won't be the case. I'll put a 1 there to indicate that the exponent is 1, which is okay because we want this exponent to be less than or equal to 1, and it is. I can't simplify the other coefficient. But you can see that it's no big deal here because this exponent here is 2, which is less than or equal to 2. So this checks for Frobenius' method. Now, we are now permitted to assume a solution of the form y equals x to the r times the summation k equals 0 to infinity a sub k x to the k. And for the purposes of taking derivatives only, it's a good idea to bring this x to the r inside and multiply it through. And we'll get x to the r plus k. Remember, this r is most likely responsible for why when we take derivatives we still start at 0, because r could quite possibly, and most of the time is, a non-integer. Well, it could be negative integers too, would still cause derivatives not to change from starting at k equals 0. If you had negative integers up here, they would differentiate forever and never zero out. So anyways, let's go ahead and throw it into our equation. I'll write our equation here, 2x squared y double prime plus 3xy prime plus 2x minus 1y equals 0. Let me go ahead and throw everything in then. This is the expression that we'll use for y, so that'll be the thing that I take derivatives of. I get 2x squared times the sum k equals 0 to infinity. So I need to take the first two derivatives of x to the r plus k. We have r plus k times r plus k minus 1 a sub k x to the r plus k minus 2 plus 3x times the sum k equals 0 to infinity r plus k a sub k x to the r plus k minus 1. And then finally I have plus 2x minus 1 times the sum k equals 0 to infinity a sub k x to the r plus k. And that's equal to 0. Now you could right now yank out the x to the r because it's already done what needs to be done. So I could pull it out front if I want to. I think before I do that though, I will multiply my coefficients through. So the 2x squared, for example, I'll go ahead and pull that in, and I'll do like I have been doing here to remind myself, or to keep myself organized, probably better than anything. First one, I get k equals 0 to infinity. I'll bring the 2 in. When you bring in the x squared, though, it'll erase this minus 2 that's up there, and I'll get x to the r plus k. On the second series, I'll bring the 3 in. I'll have an r plus k, a sub k, x to the r plus k. And this time the minus 1 will disappear because of the x, so this is turning out not to be so bad. I'm going to break this 2x minus 1 into two pieces. So I'll have plus 2x times the sum k equals 0 to infinity a sub k x to the r plus k. minus the summation k equals 0 to infinity a sub k x to the r plus k, and all that stuff equals 0. Now before I yank my x to the r out, I'm going to pull the 2x through on this second to the last series. That means pulling the 2x through. I'm going to keep it as 2 lines right now. I'll be able to combine this one later on when I yank the r out, x to the r out. So I'll get summation. I'll pull the 2x through. I get 2x a sub k. Actually, I typically pull the 2 in. I'll get 2a sub k. And then when I multiply the x to the x part of this, I'll get x to the r plus k plus 1. So far, that's the only exponent that is not playing ball with us. The last one is like the other ones were. And all that's equal to 0. Now, I have not done this before, but you can certainly combine all the series that are compatible right off the bat and then change one series later on. I think if we look at this right now, let me pull out my x to the r. And so I'll get k equals 0 to infinity, 2 times r plus k minus 1, a sub k x to the k, plus the summation k equals 0 to infinity, 3 times r plus k, a sub k x to the k, plus summation k equals 0 to infinity, 2a sub k x to the k plus 1, minus the summation k equals 0 to infinity a sub k x to the k. Probably I should block all this in there. Now let's take a look at the exponents to decide how I want to proceed next. The exponent on every series, the first, the second, and the fourth all start at x to the 0, and the last series starts at x to the 1. So I think what I'm going to do is release the first term on each of the series that start at 0. So I'm going to release one term, release the first term, on all the series that start with x to the 0 power. So I'll have my x to the r. I'll make my bracket. I think I'll start a bracket and then I'll finish it when I know how big this gets. So when I release the first term from the first series, I'm going to get 2 times r plus 0, r plus 0 minus 1, a sub 0, x to the 0, plus the first term from the second series, I'll get 3 times r plus 0, a sub 0, x to the 0. Remember, the a sub 0s are important to help us to determine our indicial equation. Minus, and this one will be a sub 0, x to the 0. And then I'm ready. All these series now will begin at 1. I'll reindex this remaining series after I rewrite these all starting at 1. And that a sub 0 that I just wrote should be a sub k. And that equals 0. Let me do a little simplifying. So on the first term here, I have 2r times r minus 1, a sub 0. Then I get plus 3r a sub 0, and then I get minus a sub 0. And then for the rest of these things, I get plus the summation k equals 1 to infinity, 2 times r plus k times r plus k minus 1, a sub k x to the k, plus the sum k equals 1 to infinity, 3 times r plus k, a sub k x to the k. Now this is where I'm going to reindex this series here. This does start at x to the 1 like all the other ones do, so I want to start it at k equals 1 just like all the other series. Of course, when you do that, when you start at k equals 1, when you go up to 1 here, I've got to subtract 1 from each of the k terms. So this will change to 2a sub k minus 1 x to the k, which matches everything else, minus the sum k equals 1 to infinity, a sub k x to the k. And that equals 0. Now, let me go ahead and collect all these terms. Let me factor out an a sub 0 from all these terms in the beginning. So I get 2r times r minus 1 plus 3r minus 1, and all of that is attached to a sub 0. Now I can finally attach or combine all of these series into one big one. And I know, it's k equals 1. I'm not doing any sort of simplifying just yet. I'm just going to catalog all these things. I have 2 times r plus k times r plus k minus 1 a sub k plus 3 times r plus k a sub k plus 2a sub k minus 1 minus a sub k. And all of that stuff is attached to x to the k. And then all of this stuff equals 0. Now everything is dependent on a sub 0, so letting a sub 0 be equal to 0 is not a good plan. Let me go ahead and multiply this stuff out here. X to the r, start my bracket. I have 2r squared minus 2r plus 3r, so I have 2r squared minus 2r plus 3r is plus r minus 1 a sub 0 plus the sum k equals 1 to infinity. I'm going to try to combine some stuff in here. I see that a sub k is attached to a lot of stuff, so I'm going to combine all that. I'll have, let me do a bracket here because it will be attached to x to the k. Let me go ahead and get all the a sub k's in here. 2 times r plus k times r plus k minus 1. And then we have plus 3 times r minus k. r plus k, sorry, and then minus 1. All that stuff is attached to a sub k, and then I have plus 2 times a sub k minus 1. That's attached to x to the k. And this is all equal to 0. So here's my initial equation. We have 2r squared plus r minus 1 equals 0. I hope this factors. Look, if the factors aren't really good, it's just going to make this a horribly complicated problem to do. So I hope it does work out. I'll start this with a 2r and an r, hoping that it will factor. I need to end with a negative 1. I think this will work. Let's see what happens here. We have 2r squared minus 2r plus r. Up, I have these backwards, so let me change this to an r plus 1 and then a 2r minus 1. Let me try it again. 2r squared plus 2r minus r makes that a plus r and then minus 1. Good. So my initial roots are r equals 1/2 and r equals negative 1. So that's, of course, what we're going to use to build on everything. We start first with either one of these. It really doesn't matter. I'll start with r equals 1/2. Now, I don't have to worry about x to the r. I'll throw that in my answer. I'm just going to look at this series right here and replace r with 1/2. So the series in question, I've already dealt with this. When r is 1/2, this leading initial term will zero out. So we're good there. Let's just deal with this series right here. And we have the sum k equals 1 to infinity. At each stage, I'm going to replace r with 1/2. So 2 times 1/2 plus k times 1/2 plus k minus 1 plus 3 times 1/2 plus k minus 1. And all of that stuff is attached to a sub k and then we have plus 2a sub k minus 1. And of course that's all attached to x to the k. And we know this all has to equal 0. Let me do a little simplifying and see if things are a little bit easier to work. This 2 will be nice because I'll be able to get rid of some halves. So let's see what happens next. K equals 1 to infinity. I'm going to multiply the 2 through to the 1/2 plus k, and that will give me 1 plus 2k. For this here, 1/2 minus 1 will be negative 1/2, so I'll get k minus 1/2 plus 3 times 1/2 plus k minus 1. And don't forget, all of that stuff is attached to a sub k plus 2a sub k minus 1. That's all times x to the k equals 0. Now I don't, well actually, you know what? Probably, when I look at this, back at this right now, I think it might not have been a good idea to multiply the 2 through. I really didn't do anything except that and hoping that it would be easy. I think what I'm going to do is this. Let me take this out of here. I've just seen an opportunity for simplification that I didn't see initially. Before just multiplying out, I'm going to notice here, I put little arrows here to indicate that I have 1/2 plus k common to both pieces. So I'm going to factor that out. So I'll pull that out. Now, at the same time, I'm going to take the 2 and multiply it through here. Now this right here is k minus 1/2. So when I multiply the 2 through, I'm going to get a 2k minus 1 on that part. Then left from this piece is a plus 3. Now this stuff comes before the minus 1 that is attached to the a sub k. And now, well, actually what I think that I should have done, this is not there. So I'm being a little bit, perhaps I'm doing a little too much at once, but whatever the case may be, this will end up becoming a 2k plus 2 inside of here. So I'll have the 1/2 plus k, then I'll have 2k plus 2, and I'll have minus 1, and all that stuff is attached to a sub k. And then as before, to make this multiplication a little easier, I'm going to take a 2 out of this 2k plus 2 and append it inside of the 1/2 plus k. Now you can avoid all of this that I'm trying to do and just simply multiply everything else out and let the chips fall where they may. But I prefer not to do these multiplications with fractions. They cause nothing but problems. So I'll get 2k plus 1 for that piece. I'll get k plus 1 for the other piece, and then I'll have minus 1. This should be a little rejoicing that should happen right now, because no matter what happens, my next line will factor very nicely, because no matter what happens here, I'll be left with the 1, and when I subtract 1, I'll only have k terms, terms with powers of k involved. Let me go ahead, and I have 2k squared plus 2k plus k, so plus 3k, and then I'll have plus 1, but then I'll have minus 1. And that's all x to the k. Okay, now what I think I'll do is, you don't have to factor this. Don't think that you have to do that, but I usually do factor it because I'm usually looking for some sort of a pattern. Nonetheless, each of these will be set equal to 0, and I'll get a sub k equals negative 1 over 2k squared plus 3k times 2a sub k minus 1. So let me do another little thing here. A sub k will equal negative 2 all over. I'm going to factor a k out of these, and I'll get k times 2k plus 3 times a sub k minus 1. And now let's go ahead and generate our coefficients. Now k starts at 1, so we'll start k equals 1. So I get a sub 1 equals negative 2 over 1 times 5, a sub 0. K equals 2, I get a sub 2 equals negative 2 over 2 times 4 plus 7, 2 times 7, a sub 1, which I can cancel these 2's out, so that's a negative 1/7. But so I'll have negative 1/7 times negative 2 over 5 a sub 0. So I have 2 over 5 times 7 a sub 0. K equals 3. A sub 3 equals negative 2 over 3 times, here we're going to have 2 times 3 is 6 plus 3 is 9. A sub 2. Of course, I can rewrite that in terms of a sub 0. So I'll have negative 2 times 2. Negative 2 squared. Not telling if this is actually going to be useful or not. Don't think, like I said, don't think you have to do what I'm doing. You can simply multiply this out. Don't worry about trying to find any patterns or whatnot. Now for the denominator, I have 3, 9, and 5 and 7. So I got 3 times 5 times 7 times 9. A sub 0. And one more for good measure. K equals 4. A sub 4 equals negative 2 over 4 times, let's see, 2 times 4 is 8, 11. A sub 3, and I can cancel something there. And then a sub 3, of course, I still have, well, I have a positive, but 2 squared. 2 squared over, now what do I have in the denominator? I have 2, 3, 5, 7, 9, and 11. Prime numbers. So 2 times 3 times 5 times 7 times 9 times 11, a sub 0. And if I'd like, and I do, I'll cancel off a 2. And this, of course, goes on forever. Remember, all of this stuff was attached to r equals 1/2. So when you're trying to figure out your solution, remember y equals c1 y1 plus c2 y2. The a sub 0s are c1. dy1 is given by, remember we have to put the x to the 1/2 out front, times, and now the rest of it is the power series that was developed by finding these coefficients. So that was 1, here I was going to start with 1 where the a0 position was, but then we have minus 2 over 5 times x, because that's attached to a1. And then attached to x squared we have positive 2 over 5 times 7 a0. And then attached to x cubed, I don't need the a0s in here, that is, the a0, as I mentioned, was accounted for inside, c1 is a0 if we like. A sub 3 is attached to x cubed, that's negative 2 squared divided by 3 times 5 times 7 times 9. And that is attached to x cubed. I think I'll make that a little bit smaller. And then finally, we have plus 2 over 3 times 5 times 7 times 9 times 11, x to the 4th minus, and that goes on forever. So there goes our y sub 1. That's half the answer. Now to find y sub 2. Go back and let's find what the other value for r was in the initial equation. R equals 1/2, r equals negative 1. Let me go back and find the expression that has r's in it so that I can figure out a way of getting these coefficients. Let's go back. I got to find instances that have r in them. And here it is right here. This is the one that I want. So I'll grab this. That way I can plug in my r equals negative 1. I don't care if I have the... I'm not going to take the xk. I don't need it. Alright, so let's go ahead and plug in our numbers. I'll have 2 times negative 1 plus k times negative 1 plus k minus 1 plus 3 times negative 1 plus k minus 1, and all of that stuff is attached to a sub k, and then plus 2a sub k minus 1. I'm going to do as I did before, noticing that I have a common factor to both pieces. And I think back of it, you could have probably played around with the format of this while the r was in there and made life a little bit easier here, but I don't think it's that big of a deal. I'll factor out the k minus 1 from here and from here. So I'll have, and then well, you'll see what I'll do. I'll take out my k minus 1. And then as before, I'm going to take my 2 and multiply it through here. Right inside of here is k minus 2. So that's going to be 2k minus 4. And then I'll have plus 3. And then a minus 1. And all of that stuff is attached to a sub k. So we have 2k minus 1. Once again, a little rejoicing occurs here because I've noticed that whenever I get done multiplying this out, the ones are going to cancel out. So let's see what we have here. I have 2k squared minus k minus 2k, so minus 3k. And as I mentioned, plus 1 minus 1, they go away. A sub k plus 2a sub k minus 1. And of course, we're going to set all of this stuff equal to 0. And now let's go ahead and generate our coefficients. So a sub k this time is going to equal negative 2 divided by, I'm going to write this out in factored form, so it'll be k times 2k minus 3. Similar to what we had before, a sub k minus 1. And now let's go through it. K starts at 1, so k equals 1 tells us that a sub 1 equals negative 2 over 1 times 2 times will be 2 minus 3 will be negative 1. A sub 0, and that's just going to equal 2a sub 0. When k equals 2, a sub 2 will equal negative 2 all over 2 times 4 minus 3 is 1 times a sub 1, so that'll equal negative a sub 1. K equals 3. We have a sub 3 equals, I should be careful here. These negatives canceled out, gave me 2a sub 0. But then when I did this one, right here, did I do it right? I did it right. A sub 1. Well, that's negative a sub 1. I need to get it in a sub 0. So that's negative 2a sub 0. K equals 3. I have 1 over 3 times 6 minus 3 is 3. Oh, I hit it from myself. Negative 2 up here. A sub 2. That'll be negative 2 over 3 squared. A sub 2 is negative 2a sub 0. So we get 2 squared over 3 squared, a sub 0. And then I'll end it off with k equals 4. A sub 4 equals negative 2 over 4 times 2 times 4 is 8 minus 3 is 5. A sub 3, I can cancel a little bit here. Interesting. So I have negative 1 over 2 times 5. And then a sub 3 had a 2 squared over 3 squared, a sub 0. Let me cancel one of these 2's. And it looks like I get negative 1 over 3 squared times 5, a sub 0. and it goes on and on. Now all of this stuff was attached to x to the negative 1. So in the answer will be c1y1 plus c2y2. I already mentioned a sub 0 in the first instance was a c1. Now my a sub 0 is c2. What is y2? y2 equals x to the negative 1 times 1. That's the 0th spot. Now what do I got in the x to the 1? I've got plus 2x. Then what comes in the x squared? I think that was a negative 2. And then in my x cubed, I have 2 squared over 3 squared. And then my x to the 4th, I had negative 1 over 3 squared times 5, x to the 4th, plus dot, dot, dot. And before I finish this off, I just noticed right here, I did have a 2 left over in that spot. So let me put it in there, and let me get it in here as well.